Yeah. So, good morning, everybody. So, at the outset, first of all, I'd like to thank today's guest speaker, Professor Kunal sir from NIT Roorkela sir. In spite of his busy schedule, when we requested, sir happily accepted, and he is having a rich experience in this particular domain. And so, we are very happy. And definitely, I hope that his knowledge will enrich to impart knowledge to our teaching as well as to pursue our research and our professional growth. So thank you so much. In regard, before start of the program, I request Sunita, the scholar of program, I request her to introduce today's guest of honor, Professor Kunal sir. Over to Sunita.
Yes, sir. Thank you so much, sir, for giving this opportunity. It is my great privilege to introduce today's speaker, Professor Kunal Pal, sir. Professor Kunal Pal, sir, obtained his bachelor degree in pharmacy from the College of Pharmacy, New Delhi, India. Sir pursued further studies, completing his ME degree in biomedical engineering at Jadavpur University, Kolkata, and earning a PhD in material science from IIT Kharagpur, India. Following this, Dr. Paul Sir served as a postdoctoral fellow at Rayan University in Canada, broadening his global perspective. In 2009, Dr. Paul Sir has begun his professional journey as an assistant professor in the Department of Biotechnology and Medical Engineering at the National Institute of Technology, Roorkela, India. His research primarily focuses on biomaterials, drug delivery mechanism, food science, and innovative food designs. Dr. Paul Sir also possesses expertise in biomedical instrumentation and signal processing, showcasing his multidisciplinary approach. His academic prowess is evident through his extensive publication record, including 308 Scopus Index research articles and 44 papers with high H-index, 3 design patents and 2 utility patents. Notably, SAR has been recognized in Stanford University top 2% scientist list for consecutive years 2022 and 2023. Dr. Paul Sar has established research collaboration with several labs within and outside India, including the Indian Institute of Technology Jodhpur, Seoul National University South Korea, King Saud University Saudi Arabia, Ojuland University of Life Science Poland, and the University of Philippines Los Baños. As the principal investigator, Dr. Palsar has secured 9 sponsored research grants in India. His recent achievements including securing a bilateral grant titled Development of a Composite Optical Device employing an artificial intelligence algorithm for evaluating the shelf life of raw agricultural products from the Department of Science and Technology, International Cooperation Division, Government of India. In collaboration with the Department of Science and Technology, Philippines. Additionally, Dr. Palsar obtained another significant grant patent developing an artificial intelligence enabled multi-spectral reflectance photography device for the prediction of shelf life of bakery products from the Science and Engineering Research Board Core Research Grant, Government of India. Thank you so much, sir, for accepting our invitation to deliver talk in our STTP program, sir. Now I request Professor Kunal Pal, sir, shall continue the session.
Thank you, Ms. Sunita. And first of all, I would like to thank Professor Kishore for having me here to deliver a lecture in the area of image processing and AI. Okay, so now I will be sharing my screen. So, can you see my screen?
Yes, sir.
Yeah, okay, good. So, good morning everyone. Today I will be talking about role of chemometric analysis for medical analysis for medical applications. Okay. So, I think there is a mistake. Role of chemometric analysis for medical application, it should be like that. Okay. So, sorry for this one. Now, whatever I will be presenting today, The work has been carried out by my PhD scholar Deblu. Okay, so before going into the details, let us analyze what is chemometric analysis. Okay, so what do we mean by chemo? Chemo means chemical. Okay, and then metric means understanding the qualitative and the quantitative aspects of any functional groups or molecules in a particular sample. Okay, so when we talk about this chemometric analysis, it is a kind of analysis where we apply mostly spectrometric analysis, which deals with our this spectral components and how they interact, how the electromagnetic radiations they interact with the certain molecules or the functional groups, and then we apply various statistical measures including machine learning models to get some insightful information about the physical process or the chemical process that is undergoing within the sample. Okay, so before divulging into the main topic, what I would say is that I will be discussing about the spectroscopic techniques. So what do you mean by this spectroscopic techniques? Basically, in spectroscopy what we have is that we have an electromagnetic radiations, so they interact with the sample. Okay, so all of us know that the electromagnetic radiations, they are nothing but the synchronized oscillation of electric and the magnetic fields. Okay, so what are the different kinds of electromagnetic radiations? The different forms of electromagnetic radiations include the radio waves, microwaves, infrared waves, visible light, ultraviolet rays, X-rays, gamma rays. So when we talk about the radio waves, we have this MRI spectroscopy or MR spectroscopy, magnetic resonance spectroscopy, where we use the radio waves as the interacting electromagnetic radiations. Then in microwaves, so in ESR, electron spin resonance spectroscopy, we use the microwaves. Then infrared is being used in infrared spectroscopy. So there are two types of infrared spectroscopy majorly. First one is the near infrared and the second one is the mid infrared region. Okay, so next, the visible light spectroscopy, we all know, most of us have the UV visible spectroscopy in our laboratory. Then ultraviolet spectroscopy, where we use the ultraviolet rays. Then we have the X-rays, which are being used in various spectroscopic technique like X-ray fluorescence and also in the XRD analysis. Then we have gamma spectroscopy, where we use the gamma rays. So what all these electromagnetic radiations they have in common? All these electromagnetic radiation, they contain some amount of energy. It may be having a momentum and also the angular momentum. So in general, you can say electromagnetic radiations, they have packet of energies, and now this packet of energies, they interact with the matter. And in spectroscopy what we do is that how these electromagnetic radiations, they are interacting with the matter, this is being studied. Okay, now this is the electromagnetic spectrum. So over here you can see we start with the radio waves on the left hand mode side, and then we go towards the gamma rays. As we move from left to right, what happens is that the energy content, it increases. Okay, apart from that, if you look into the system, since the energy increases, and if you look from left to right, the size of the atoms or molecules or subatomic particles what we want to analyze, it reduces significantly. Say for example, if you look into the visible range, in the visible range we are basically looking into the interaction of the electromagnetic radiation with the microscopic world, say for example protozoa, bacteria and other things. As you go towards the ultraviolet rays, we are analyzing molecules. As we go towards the X-ray, we look into the atoms. If we are using gamma rays, then we are basically analyzing the atomic nuclei. Okay, so in this way, if you see the different electromagnetic radiations, they provide us different information. Okay, now this is a very interesting diagram, which is basically the energy level diagram. In the energy level diagram, what happens, if you see, there is a ground level given by this E0. Over here we are having a lot of levels, V0, R1, R2, R3, then V0, V1, V2, V3. So all these things, they are regarded as the ground state energy level. Okay, so in UV visible spectroscopy, what happens, electrons that are present in the E0 ground state energy level, they move to the excited state of energy. Okay, so there is a movement of electrons. Okay, on the other hand, when you talk about the movement of the molecules, so if you have listened me carefully, I have talked about that the movement of electrons in the first instance. Okay, so from E0 to A1, when we go, and when we have this visible light and the UV ultraviolet light radiations, when they interact with the matter, there is an electronic transition because electrons are moving. On the other cases, say for example Raman and IR spectroscopy, these vibro-rotational energy levels, they come into play. V0, V1, V2, V3, they are the vibrational levels. So from one vibrational levels, the molecules go to the another vibrational levels. Okay, here I am talking about the molecules. Okay, molecules having a specific vibrational level moves from a specific vibrational level to another vibrational level. Also molecules, they may rotate, and due to that rotation we may have the rotational energy, and herein the rotational levels are R1, R2, R3, R4. Okay, so if you look over here, what is happening in the electronic transition, we need the highest energy. In the vibrational energy, we need the medium kind of energy in comparison to the electronic transition and the rotational transition. And the rotational transitions, the transition would be needing very low amount of energy. Now if you go back, if you see visible, ultra visible, over here we will be having electronic transitions. Infrared, we are having this vibro-rotational energies which are associated with the infrared spectroscopy, in both type of infrared spectroscopy, near IR and the mid IR infrared spectroscopy. Okay, so if you see, so as there is a change in the energy level, the type of interaction, the type of interaction of the electromagnetic radiation with the matter, it changes, and there are different types of interactions which may be going on. It may be electronic transition, it may be vibrational transition, it may be rotational transition. Okay, now for the visible light spectroscopy, commonly the xenon lamps, they have been used, and if you look over here, what happens is that we are having a broad spectra. We are having a broad spectra over here, right? Then in chemometric analysis, the selection of the spectroscopic method, it is quite important. Now if you see in UV visible, we are basically interested in the absorption and emission spectra, and herein, as I already told you, we are dealing with the electronic transitions. In NIRS, near infrared spectroscopy, or mid IR spectroscopy, we are mainly dealing with the absorption spectroscopy, which are basically interacting through the vibrational or the rotational energy levels. Okay, so over here we are basically interested with the absorption of the radiation. There is another type of radiation which is regarded as Raman spectroscopy, and it was being proposed by Sir C.V. Raman. Okay, and it is herein, in this Raman spectroscopy, the scattering of the electromagnetic light, they are being analyzed. And lastly, the NMR spectroscopy, we have the absorption of the radio waves, which plays an important role. Now coming to the spectroscopic techniques again, as I told you, these are the different types of spectroscopic techniques, and herein we are having different wavelength ranges and what we can analyze. Okay. So one of the common spectroscopic or the chemometric analysis is use of any signals. Herein the example has been showed that the surface enhanced Raman spectroscopic method has been employed, and from there we get the spectral data, and then we apply the artificial intelligence to unravel the underlying signals that are present in the mixed signals from the spectroscopic data. Now these isolated signal components, they are used to analyze the microbiological data, forensic data, medical diagnosis, foodonomics, and pharmaceutical in the pharmaceutical industry. Now any type of spectroscopic techniques, they can be of two types. One is transmission, where the radiations, they move through the sample, and on the other side of the sample we will be having the detector. So one side we are having the radiation source, and on the other side we are having the detector. There is another type of spectroscopic technique which is regarded as the reflectance spectroscopy, wherein both the light source and the detector, they are on the same side of the samples. So electromagnetic radiations, they fall onto the sample, and again from there the lights are reflected back into the sensor. Over here, if you look into the centermost darker portion, over there we have the imaging sensors, and from there we can collect the signals and we can get the spectral information. Now what is chemometric analysis? I already told you what is chemometric analysis, but let's see the exact definition. So chemometrics, it combines the power of advanced statistical techniques and machine learning algorithms to tackle the complex challenges inherent in spectroscopic analysis, such as optical spectroscopy, chromatography, and mass spectrometry. What are its roles? The roles are medical diagnostics, drug discovery, biomarker discovery, and therapeutic monitoring. Okay. So over here again, if you see that there is a Raman probe, we are having a sample. From here we get the peaks. So using this peak, we may apply the various statistical techniques like principal component analysis or independent component analysis. Also other machine learning models, they may also be included over here to gain information about the chemicals that is being analyzed. Okay. Now what we are doing at NIT Rourkela, the first in the first study, what I would be discussing about, the development of a low cost crystallization monitoring system. So herein we have developed a system which can analyze the crystallization of the fat molecules in oleogels. So what are oleogels? Oleogels are basically semi-solid materials that are used for structuring of oils, and they have been commonly used in the biomedical or the pharmaceutical industry as drug delivery vehicles. Okay. So if you look into the drug delivery systems, they form a critical aspect in the field of biomedical industry. Okay. It significantly impacts the efficacy, safety, and overall success of the therapeutic interventions. Okay. So due to this reason, we wanted to develop a system which can help us in monitoring the oleogel crystallization process, the fat crystallization process in the oleogels, because how the crystallization happens, it has a direct relationship on how the drug will be released from the oleogels and also the drug's bioavailability. Okay. So what are the aspects that needs to be analyzed while we are monitoring the crystallization process? Through the analysis of the crystallization process, we can analyze the drug release rate, we can analyze the drug stability, we can analyze controlled release efficacy, and the encapsulation efficiency. So all these three things can be tailored if we are able to tailor the crystallization process. Hence, we wanted to develop a system which can help us in monitoring how the crystallization of the fats they are being tailored. Okay. So, development of a color-based process monitoring system. So, the development of the device, it has been accepted in the and published in the Journal of Food Engineering, which is one of the peer-reviewed journals from Elsevier and having an impact factor of more than 5. So over here, if you see, we have initially developed a standalone colorimetric device. So if you look over here, we have taken the Raspberry Pi, then we are having a camera, a light source and a temperature sensor. Okay. So why temperature is needed is because we want to analyze the reflectance property of the samples as there is a change in the sample temperature during the crystallization process. So this is the overall 3D model of the developed prototype, and this is the model of the prototype which has been developed in the lab. Now this is the software for the colorimetric device, how the colorimetric device it works. So initially we have to do the initiation of the device where we need to calibrate the imaging sensor. Okay. So the grayish boxes, they indicate the front end process, and the yellowish boxes, it shows the back end process that is going on in the software. Similarly, in this process there are two modes. One is the quality testing mode and the other is the process monitoring mode. In the quality testing mode, what you can do is that you can bring several samples, and those samples can be analyzed one by one, and all the data will be saved in a CSV file. In the process monitoring mode, we can analyze the process of any given system, say for example the crystallization temperature, okay, crystallization process of the oleogels. So this is the flow diagram of the crystallization process monitoring system. Now this is the main software that has been developed. So first one is the calibration panel. First we have to calibrate this system. Then we have this test panel. Over there we are having this quality testing and the process monitoring testing. So this is the test panel for the quality testing, and the second one, it is the test panel for the process monitoring system. Methodology. So we first standardize the device using the colorimetric method, wherein we have used 7 play cards with known color parameters, and we have compared it with that of its standard device that is available in the market. Then in the gelation kinetics, we analyze the capability of the device to monitor the process by monitoring the gelation kinetics of molten oleogels, okay, when the samples were incubated at 5 degree, 15 degree and 25 degrees centigrade. Then crystallization process monitoring. So the crystallization process was monitored using the developed device and the DSC instrument, and then we have performed the correlation study to find out the similarity between the test and the between the readings what we have got from our device and from the DSC instrument. Okay, so there is a spelling mistake over here, please excuse me for that. And lastly, to find out whether we can use this in real time system, we have taken a fat system, that is the butter sample, for understanding whether our system it can be generalized for most of the fat related systems. Okay, so herein also we have analyzed this butter sample using the developed device and the DSC instrument, and then we have tried to correlate the instrument data. So results. So this is the calibration, how you do it. First we do it with the black play card, then with a white play card. Then when you put in any sample and try to measure the color, so we get the readings something like this. So herein we have the synthesized color after the imaging system, it has imaged the sample. Okay, over here you can read the a particular region of interest. You can select a particular region of interest to read the color parameters. On the right hand side you have the original placard details through which we have prepared the placard. Then we have the color details acquired from the commercial device, and then we are having the details acquired using the developed device. In the delta E, which is a measure of the difference between the color of with the original details and the color perceived, if you see with our device, the delta E was much lower as compared to the color details acquired using the commercial device. Okay. Now next comes the process monitoring with temperature. What we did is that we took the samples, we heated it at 90 degrees centigrade and put it into the colorimeter. So it looks something like this. So this is your temperature sensor which has the PT 100 within it, and then it has been digitized. Then as the temperature reaches at around 50 degrees centigrade, it starts recording the sample temperature, and as the time progresses we record the temperature and take the image of the samples so that the color parameters can be generated, and from those color parameters we can generate the intensity versus the time graph, and we can use that for the analysis purpose. Okay, like that you can generate other types of plots also. If you see in the A image, we are having hue over here. From this drop down menu we can also select the other color parameter whatever you want to measure. Say for example, we are having hue, saturation, intensity, then L star, A star, B star, then yellowness index, whiteness index, color difference. Whatever the plot you want, you will be able to generate. Here we have just shown the diagram with the intensity. By default the intensity versus the time plot will be plotted. However, at the end of the process you can generate the other plots. These are the results which have been collected at the end of the process. Okay. So gelation kinetics, if you see that we have recorded the temperature versus the time parameter, and we have marked the different processes where we have this primary crystallization started and where the primary crystallization it ends. Okay. Then we have, since if you look into all these profiles, they look like an exponential decay model, decaying function. Hence we model the gelation kinetics data with the exponentially decay model equation, and we got all this parameter. Okay, so from here you can find out the crystallization rate and also the onset which is from the exponential decay model, and also from the graphs we can collect the temperature versus the time information. Now for the crystallization process monitoring, we have taken the L star versus the temperature graph over here. So this is for the 5 degree, then the second one is the 15 degree, and the third one is the 25 degree centigrade. So the first one, it is before the first box we have the nucleation stage, where the several molecules of fats, they are basically aggregating to form the nuclei, and after the box 1 the primary crystallization starts, and thereafter after the box 2 the secondary crystallization or the consolidation stage it may start. So if you see in all the samples this is happening. Okay. Now from there again we can find out at what temperature the primary crystallization starts and at what temperature the secondary crystallization it starts. Now next what we did is that, as I told you, we tested it with a butter sample so that we can be confirmed that we are getting a thermal profile which, or the data what we are getting, that can be generalized across a number of samples. For that reason we took the butter sample. And if you look over here, we are having box 1 and box 2. So correspondingly, if you look into the DSC, we are having two peaks, endothermic peaks, exothermic peaks in the DSC curve. Okay. So these are the images at different temperatures, how this how the sample looks like during the crystallization process. Okay. Now the summary of this work: we have developed a dual operating system wherein the color parameters can be acquired not only in the testing mode but also in the process monitoring mode. So we have already filed a patent over here, and a fiat has been submitted, and we are waiting for the result, final result from the patent office. And secondly, a design patent from this work has been put up. Now, development of ML enabled spectrometer cum colorimeter for detecting spoilage. As I told you that chemometric analysis is basically an analysis where the spectral components are being used. What do you mean by colorimeter? In colorimeter, generally we are having red, green and blue. That means we are only having 3 color parameters. That means we are having only 3 spectral components. However, if we can generalize the system so that we can get multiple spectral data, then we will be able to develop a low cost chemometric analysis system in the visible range. Okay, keeping that in mind, what we did is that we did some modifications in the previous colorimeter so that we can get spectral data from the system. Okay, so what are the developments or the changes we have made? Initially, if you see, we had Raspberry Pi which was inbuilt within the colorimeter. However, herein we have got rid of the Raspberry Pi, and we have replaced that with that of a computer. Why that is so? This is because when we try to generate the spectral components, the computational requirement, it is quite high, and the Raspberry Pi, it was not able to do that much of computation. Okay, and it was making the system slow. So the first thing what we did is that we eliminated that. Okay, now when we eliminated that, our system, it looked something like this. Now coming to the background, so if you see, according to the WHO, around 600 million people, they fall ill, and usually 4,20,000 die annually due to the foodborne disease, many of which are linked to the spoiled food. So this results in the surge in the hospitalization. Okay, so this makes the detection of the food spoilage as an essential parameter, because it can help us to prevent the gastrointestinal diseases, infections, and even the chronic conditions that are associated with the consumption of the spoiled food, especially in the rural setup. And by doing this, we will be able to reduce the potential delays in the healthcare system. Okay, in this context, the global food security is of utmost importance, and therein the spoilage detection is key to reducing not only the food waste but also to reduce the potential delay in the healthcare system. So these are some of the degradation processes which are associated with the spoilage of the food products. And then if we consume this thing, we can have food poisoning, and may have to take medicine, and we may have to undergo several morbid conditions, and which may lead to hospitalization also, right? So hardware development. So this is the picture of the hardware, and this is the complete setup what it would look like. So again, the software for the spectrophotometer cum colorimetric device. So this is the flow chart. Then methodology, what we did is that we took braid samples for the analysis, and then we tried to develop or analyze these braid samples. So the first one, it is a control sample, and in the next 3 samples we added 1 microliter of clove oil, 10 microliter of clove oil and 100 microliter of clove oil on the lid of the sample holders. Okay, so clove oil, as you all know, it is an antimicrobial agent, and when we will close this system, it will form vapors, and those vapors of the clove oil, they will be able to restrict the microbial growth. Okay, so what we did, first we did the colorimetric analysis, then we did the spectral analysis, then we conducted the microbial study, and lastly we developed the ML models. Okay, now what happens is that we used this colorimetric and the spectral data for ML based classification, and then we went for the deployment of the model. So ML modeling, first we did the data collection, then data pre-processing, then we chose the ML and the training models, then we evaluated the models, and lastly we went for the predictions. So in the ML based model in ML based classification, we went for 2 types of models, supervised learning and the ensemble learning models. In the supervised learning, we are having this random forest, SVM and decision tree, and ensemble learning models, we had AdaBoost, gradient boosted tree and XGBoost, extreme gradient boosted trees. Okay, so out of these 6 models, base models were selected and employed in the device for the early detection of spoilage of the braid. So data pre-processing, when we collected the data, we were having 12 color parameters and 36 spectral parameters, so which constituted 48 features, and then we went for the data integration, then we went for the feature selection. In the feature selection, we went for the forward selection method, wherein we used 5, 7, 10, 15, 20, 25 number of features sequentially, and during that process we changed the models in between RF, SVM, DT, AB, GBT and XGB, and we found that 15 features when we used the XGB, that gave us the highest accuracy. So we selected this 15 features which were being generated by the XGB model during the forward selection process as the new data set for further analysis. So over here in the new data set, what you have is that 6 color parameters and 9 spectral parameters. Then we went for the model training and testing. Using the new data set, what we did is that we went for the training set. In the training set, we used the control sample. Similarly, the control sample data were used in the validation test also, set also. So when we went for this training set, we used this model hypertraining and training, we changed the model hypertraining and training parameter by adjusting the hyperparameters, and we employed RF, SVM, DT, this AdaBoost, GBT and XGB, and hypertuning parameters with grid search CV it was used. So from here the model with base parameters it was selected, and in the validation the model validation was done, and then we did the testing, and in the testing set was selected as S1, S2 and S3, which consisted of the clove oil as the antimicrobial agent. So overall we had a 288 number of the data set. We used 230 for the training purpose, and for the validation purpose 58 sets were used, and then we tried to deploy it. So this is the chemometric analysis. So if you look into the chemometric analysis, we are having all the AI techniques that may be employed, but we have restricted ourselves to a specific system. Okay, so coming to the results, so this is the software, what it looks like, and then in the spectrometer we are getting the spectral component along with the color parameters, and then herein on the right hand side in the figure 24 you can see the spectral components from the standard device and the developed device, they have been shown over here. So this is the analysis of the color parameters. So in the color parameters, if you see different color parameters, they have been analyzed, and in most of the cases, if you see in the control, the control sample, it is showing very significant difference in the color parameters at the day 10. Okay. Now this is then we perform the spectral analysis. In the spectral analysis, if you see as the day progressed, there was a considerable reduction in the percentage reflectance. Okay. Then this B1, it is due to the S1, then C, it is due to the S2, and D, it is due to the S3, and these are the days. So in all of this, if you see, so what is happening as the days are progressing, there are certain changes in the color parameters. Okay. Now through the microbial study, we found out the total viable count, and through the total viable count, what happens is that why it is needed? This is needed because we want to find out what is the number of colony forming units of the microbes that are present within the bread samples. So as per the literature, if you see, so TVC, if it is below 8 into 10 to the power 4 CFU per gram, then it is regarded as fresh. If it is in between 8 into 10 to the power 4 to 1 into 10 to the power 5, then it is regarded as early spoiled, and anything above 1 into 10 to the power 5, it is regarded as the spoiled. So here is the microbial culture plates that have been shown to you. Okay. Now herein, if you look into this table, so in the control sample, if you see at day 8, the sample is getting early spoiled, and day 10, the sample is getting completely spoiled. On the other one, in S1, at day 8, the sample is early spoiled. Also in day 10, it remains as early spoiled. If you look into S2 and S3, at day 8, due to the inclusion of club oil in higher proportion, at day 8 also the samples remained as fresh. Okay. However, on day 10, they became early spoiled in nature. Now we had these machine learning models that have been developed. Now if you look over here in the ML models, the RF model, it showed an F score of say around 90%, and XGB, it showed an F1 score of 92%. Okay. So we selected these two models and we looked into the other parameters, and these are this error curve. If you see, none of them, they are crossing each over. That means there was no overfitting of the data. Okay. So these are basically the ROC curves. Okay. Now here, if you look into these testing accuracies, in S1, what we are having in day 8 and day 10, the samples were early spoiled. So in RF, if you see, we got a higher number of data. Okay, this classified data. Then in S2, if you see, day 8, it was fresh. If you see over here, it is fresh, and then at day 10, the samples become early spoiled, right? Similarly, and S3 also, we had fresh sample at day 8. Also in S3, if you see, through the microbial count, we found that it was fresh, and then in day 10, the samples became early spoiled. Okay, this is the table which we got from the TVC. Okay, here we already reported here, right? So that has only been represented over here again, so that we can compare the results in a proper way. In XGB also, if you see, the similar kind of stuffs we have got. Okay. Now, however, if you look in XGB, our classification accuracy, especially in the S1 class, it is better as compared to the RF. Okay. Now, here in the summary is the device what we developed. It is having a dual function where we can develop the color and the spectral components, and these color and the spectral components, they may be used for chemometric analysis. From the microbial study, we have seen that at the end of the 10 days the control samples it got spoiled. However, S1, S2 and S3 they remained at an early spoiled stage. This indicates that addition of clove oil it is delaying the what you call this spoilage process of the bread. Okay, then sorry, then among all the ML models that we have tested, we have got random forest and XGB models which showed a better accuracy as compared to the others. And among these two models, the accuracy of XGB it was slightly better as compared to the RF. When we went for the device testing of the trained models, all of them it showed an accuracy of more than 80%, which is quite phenomenal. Now, if you look into the this computer controlled system what we have developed, it can be developed at a price of 20,000 itself, whereas the standalone model it can be developed because we need this Raspberry Pi and other important things. So that would increase the cost to around 60,000. Okay, which is much lower as compared to the marketed colorimetric and the spectrometers, which are say at least we are having 7 lakh of the price. Then this there is a Hatch Make in India, it is having a price of 1,70,000. Then X-Rite, which is an US based company, it is having 15 lakhs price. In Hunter Lab, the spectrometer it is having a price of approximately 17 lakhs. Okay, so our notable collaborators, we have collaborators from different institutes across India. Apart from that, we have some notable international collaborators from across the globe also, who help us in doing our research and share their ideas with us for in various aspects of our studies. And accordingly, if you look into our group's research capabilities, our group is working on a wide varieties of areas. We are working in the field of food science, we are working in the field of biomedical, hardcore biomedical industry like tissue engineering, drug delivery, and so on. Okay, so this is our YouTube channel. If you want to know what our group they are doing, you may be interested in joining this. You will be getting a lot of information over here also, especially on the subjects what I teach in the UG and the PG levels. Okay, so teachers thrive on the success of their students. So what I have presented, it has been the work of one of the student, but if you look what I publish, most of the things they are basically the work of my students, and since they work, I am able to present their work in front of you. With this, I would like to thank you all for your patient hearing. Thank you. If you have any questions, I will be happy to answer those.
Thank you so much, sir. I request all the participants, if you have doubts on this topic, please discuss with Professor Kunal Pal, sir. Sir is waiting for answering your question. Please utilize this opportunity. I request all the participants, please quickly ask your questions.
No questions?
Please, participants, please may ask your questions if you have any. Sir, I'm Sunita, sir. This is scholar under
Yeah.
Professor T. Kishore Kumar, sir. Sir, I am working on biometrics, sir. ECG based biometrics, sir.
ECG based.
Yes, sir. Yes,
Okay,
sir.
okay, okay. Good. So, what you are working on?
Yes, sir.
What you are
Uh,
working on basically?
Basically,
What you are trying
sir.
to do? From the ECG, you are trying to biometrics. It has a wide field.
Yes, sir. Yes, sir. Actually, we are implementing one CNN network, sir, to extract the unique features from ECG signal to recognize a person, sir.
Okay, okay, okay. Good, good.
So we are developing architectures, sir.
Okay, good, good.
Um,
So, anyway, it seems everyone has understood everything, or may not have understood anything. So,
yes.
this may be if participants are not asking questions. This is either they have understood everything or they have not understood anything.
No,
So I
sir, your session was very
hope.
informative. Much
So
knowledge, sir. It is a new concept, sir, for our participants, sir.
yeah,
Uh, yes, sir. Thank you so
yeah.
much, sir,
Thank
for
you.
sharing a wonderful knowledge to us, our participants, sir. Thank you. Thank you for your contribution to success of our program, sir.
Yeah,
Thank you
thank you,
so
thank
much,
you,
sir.
thank you for inviting me. Bye. Give my
Yes,
regards to Professor Kishore.
yes,
Yeah,
sir. Thank you, sir.
bye.